Okay, you know, another bonehead thing, I corrected it by, putting squares here where they should have been. Okay? And I know darn well what I should have written down, I just wrote it down carelessly again. This is A1 plus A2, not A1 plus B1, right? And this is B1 plus B2, but I wrote A2 plus B2. It's A1 plus A2 and B1 plus B2. And I didn't recognize the error until somebody said, but I got A1, B1 plus A2, B2 here. I said, well, it can't be, because if you go up to this expression and square it, and then I saw what I'd done, okay? So, just, like I said, keep an eye on me. If you write it down according to what is here, you're going to get this, and it's going to give you this. And clearly you're going to get it, and I think the rest of you will too, okay? But be careful about your algebra. And also be careful about what you write down, like I'm not. Okay, so we get this. Now, the point is then that this is what we define as, make sure I write the right subscripts on the right letters in the right positions, okay? Vector A1B1 dot A2B2. This is called your dot product. And it is equal to A1, A2 plus B1, B2. So, among other things, test for orthogonality at least in R2 has just been proven. Actually, we haven't totally proven it. Okay? I'm stating this as an if and only. If what was shown is that if they're orthogonal, this is true. But you can do the reverse. If this is so, then they have to be orthogonal. Okay? And there are various ways you can prove that, and then we'll worry about that, and I'll probably ask you to see if you can prove it the other way. Okay? So you've got all the stuff you need. You just have to twist your logic around to even understand why you've got to prove the opposite thing. Okay? Okay, so, for the opposite thing, the converse. Okay, test for orthogonality is this, but there's more. This gives us more. First place, this can be extended to Rn. Okay? And you just use mathematical induction. It works in R3, and then we just declare that it works in Rn. Okay? You just match up the components of your vectors and multiply them together and add the results. That's your dot product. Very simple. Easiest calculation there is, other than maybe adding two vectors or something. Okay? There's more. Started to write this as a numerator because the way it's usually used is to figure out the cosine of an angle between two vectors. That's the way I actually tend to think about it because that's the way I usually use it. But let me write it out. Nothing wrong with what I wrote out, except I was starting to write this as a numerator. Now I'm trying to write V as W. I'll get it right here in a minute. V dot W is the magnitude of V multiplied by the magnitude of W times the cosine of theta, okay, where theta, see, I go between the vectors, okay? So now if I give you two vectors, you can easily write down what the magnitudes are, okay? And you can easily write down the dot product, so you can easily find theta. Okay? So I'm going to, some of the exercise I'm going to give you this weekend, going to be doing that, okay? So we have a test for orthogonality. We also have the ability to get the angle between two vectors. Now it gets weird because now we can find the angle between two polynomials, provided we define our dot product, okay? And it's not actually a dot product, we're going to call it an inner product. It's going to involve a simple integration, just integrating polynomials.